Hello, everyone, and welcome back. I'm Jack Rincon here with Dr. Pepe Ping, and we are delighted to host today's session in the Bridge to AI TRM Working Group Lecture Series for 2025 to 2026. This series is part of our broader effort to bring cutting-edge advances in large language models to the entire consortium and beyond. Today, we're excited to introduce lecture number 5 in the LLM module focused on spatial intelligence, a key to embodied AI. We're grateful here. We're grateful that you're here, and we look forward to giving you guys a great presentation.
So thank you, Jack. Our distinguished speaker today is Dr. Parisa Kordjamshidi. She is a faculty member in the Department of Computer Science and Engineering at Michigan State University. Her work spans AI, machine learning, spatial reasoning, and multimodal language vision systems. Today, she'll be presenting her lecture on spatial intelligence, a key to embodied AI. This is a very important AI machine learning domain that we have not covered in our education module before. It's my great honor to do this brief introduction for Dr. Kordjamshidi. She truly is a leading expert in the intersection of AI, NLP, and neurosymbolic reasoning. Since joining Michigan State University in 2019, she has built a highly productive research program specializing in multimodal and spatial reasoning methods for next-generation AI systems. Her work is now broadly recognized. She has won important awards, including her NSF Career Award, the Amazon Faculty Research Award, and the very prestigious Fulbright Scholar Award of 2025. And in coming years, she will be the Bloomberg Scholar visiting faculty appointment in New York. You can see her scholarship spans top-tier venues across AI and NLP. She serves on editorial boards and leadership for journals and conferences. Her work has helped making important contributions to shape the direction of our field. I'm excited to have her and looking forward to her lecture on spatial reasoning, compositional generalization, and multimodal AI. Welcome, Parisa.
Thank you. And then I'll just kick off the learning objectives real quick for you guys. In today's session, we'll walk through core learning goals. First, we'll venture to clarify what spatial reasoning and spatial generalization mean in the context of AI development, distinctions that are essential for any system meant to operate in the real world. And second, we'll examine the current limitations of large vision language models and why these gaps matter, especially as we move toward more trustworthy and grounded AI systems. And finally, we'll explore neurosymbolic modeling approaches and how integrating symbolic structure with deep learning can significantly enhance or has potential to significantly enhance a model's ability to generalize. These concepts are increasingly important as AI applications expand into healthcare, robotics, and other settings. Without further delay, I hand it over to Dr. Kordjamshidi.
Thank you very much, Jack, and thank you very much, Dr. Pepe, for a very kind and nice introduction. I'm really humbled and pleased to be invited here to give this talk. And as you mentioned, I'm going to talk about spatial intelligence, a key to embodied AI. So I'm going to explain and give the motivation using this example. This is an example of a problem that many people in vision and language are familiar with. It's called visual question answering. In this problem setting, we actually have an image given to the models and a question in natural language form. Here is an example. Is the red bike to the right or to the left of Asian people? And then the model, actually, this is taken from a model in 2019, so many years ago. And the model actually there is giving the answer right. And human also, ground truth human answer is also right. So if you look at this image in 2D, this red bug is to the right of the Asian people. So this is very impressive because the question seems very kind of complex, needs to understand objects, relations, and all. But at the same time, we were asking and probing the model to test if the model is able to answer similar questions. Like here, if we ask, is the red bike to the left of the Asian people? Is similar question just rephrased? And you see that now the ground truth human answer should be no, and the model actually answers wrongly as yes. So this is the time that we actually we have to think, does the model really understand object attributes and spatial relationships? So this is a bit worrisome because these questions are really similar. So now you might say, okay, this is 6 years ago, and given the progress in AI, this is kind of ages ago. And nowadays we have huge models with much larger sizes than we were testing like 6 years ago. We have models are augmented with a lot of paraphrase, even questions in the training data. And the sizes, the data sizes and model sizes have increased. So perhaps the model are doing much better now. So now I'm going to show you a few years later another example. This is a very huge model, 12 billion parameters. It's called DALI. The first time it was introduced, it was around 2023. And I was asking DALI to generate or visualize a sentence as follows, like a woman with an apple in her left hand standing to the right of a car. So this model is kind of called diffusion model and can generate images. And you see that there is a woman, there is an apple, there is a car. This is great. But actually the apple is always to the left hand of to the right hand of the woman. And then you see the position of the car and woman is kind of random, is not really always to the right. So this is then, again, you might say, okay, this is old now, 2 years passed. Now I'm going to actually give this question again to the much more advanced model. This is ChatGPT, which using GPT-5 features in the background and uses GPT-4o for image generation. And you see, okay, the image actually is much nicer. So you see the woman is much more natural face, and the apple, the background is natural. The car looks more natural, but then the same issues, the spatial relations, the right hand, left hand is all confused. So maybe this is a few weeks ago that I did this exercise, but maybe you can actually do it today, even if it is wrong today, maybe tomorrow or few months later, the model can solve this problem. But the point that I'm trying to make is that can we feed all possible problems and all possible solutions to these models through just generating more and more data? Isn't the world dynamic? If a problem, so if we give even full problems and solutions to the model today, tomorrow we will have new problems that the models have to help us to solve. So humans actually don't get all these possible problems and solutions. The humans get the basic reasoning skills, and they can do composition of the basics and come up with generalization and solving more complex problems that they have not observed in the past. So that is why I'm trying to argue that actually the current vision and language models suffer from this issue of generalizability in basic reasoning skills. They lack interpretability. We don't know why the first question is answered correctly and a similar question is answered wrongly. We don't know why the apple is in the right hand. Is that because all the people that observed by this model and the images observed by this model are right-handed, that is the majority. Is that the frame of reference is confusing for the model? This right of the woman would be the left of the image, and so on. So that is, we lack interpretability here. We know that with increasing data, we can always improve, but that is actually, I think it is a problem in many applications in NLP and vision, that we assume the models actually are doing very successful. We see in this kind of safety specific or critical applications, we still have to deal with these challenging problems. So given this introduction, I'm going to talk about our research that we try to touch upon from multiple aspects on this kind of reasoning problem. So I'm going to talk about what is the spatial complex multi-hub reasoning, the issues of frame of reference, and then I'm going to talk about more general compositional reasoning and generalization, point to some applications that we did like vision and language navigation, and then talk about more generic frameworks that we're proposing, and is called neurosymbolic frameworks. So let me start with multi-hub spatial reasoning. So when we had this new generation of large language models rising, many people started to evaluate different capabilities of the language models. And in my group, we started to think about, can these models do spatial reasoning or spatial information extraction? This was more historical for me because I was working on the spatial information extraction from my PhD times many years ago. And then when we had this generation of language models, we were thinking now maybe these models are really, the problem is solved and these models can solve the problem. So we created benchmarks for this domain, and the benchmarks included synthetic domains like this image. We had natural language explanations of these images, like we have three blocks, A, B, C, A e to the left of B, B is inside C, and then we have questions like, is block A to the left of block C? So the model needs to answer this question, so we evaluate the reasoning through this question answering. We also had realistic data sets, like a statue spread arms on a hill is like real images, and then we have questions like, is the statue above the hill? Just to summarize the results that we had at the time, this is a few years back, we realized actually the models had really difficulty for answering these questions, even in synthetic domain. And this was the time that for Wikipedia-like questions, 2019, 2020, for Wikipedia-like questions, we had models that had really 95% accuracy. But then on this synthetic data set with like vocabulary of 40, 50 words, we could get like 70% accuracy for these multi-hub reasoning questions. So this was a bit surprising at the time, and we tried to actually improve the models by generating synthetic data. And then, of course, we could improve a little bit by feeding more data to them. But we were thinking like how we can really train the models in a better way that they can have more generalization for understanding spatial logic. And I'm going to explain you what I mean by spatial logic. So look at this piece of rule. Actually, we have left A and B, or object 1 is to the left of object B, then object B is to the right of object A. So if I want to train the model to follow these rules, perhaps I need to generate thousands of objects in indoor scene, outdoor scene, tables, chairs, I don't know, like buildings, cars, and then to practice these left and right relationships, and then teach the model to obtain this kind of knowledge through learning from data. But actually, we know that there are a handful of rules that we know this is kind of a spatial logic, and it's independent from indoor, outdoor, or even independent from the type of the objects. So maybe we can have a better way to actually exploit this knowledge more efficiently and help the models to generalize to any environment, add this for this kind of simple kind of reasoning. So following this idea, we tried to do kind of some training paradigm that helps to exploit this kind of logic as a source of supervision for training the model or tuning the models. So here I'm going to explain what we did. We use still data, so we have our synthetic data with what I call context. The context explains images like this. The image is not used in this setting. We are focusing only on textual question answering. The image is just for the sake of explanation. The context is there are three boxes. White is above orange, as you see, and the red is above white. Now the question is that is orange below red, right? And the model needs to just simply do some transitivity relationship to infer that, okay, the orange is below red. So we have this data, and then since the data is synthetic, we could control and actually generate the sequence of the chain of reasoning for going from the premises to the conclusion. For example, if I know that white above orange, then I have a handful of spatial logical rules like above x and y, below y and x, similar to what I showed before. And then I can infer based on rules that orange is below white. And if I continue this, then I say below x and y, below y and z, then below x and z. And then I can conclude orange is below red by transitivity. So here is all the type of the data that we are having. Now we wanted to use this data to be able to help the models to do this kind of logical reasoning. So the way that we try to do this is like, okay, we have this chain of reasoning. Now we're going to actually push the model to follow this logic by not violating this chain of reasoning. And what I mean by that, we want the model to answer the question correctly, of course, that is how we train the models, but also we want the model to be consistent. If the model says white above orange, then it should say orange below white. So that's why I'm generating these rules, and then based on this chain, and then I'm going to, sorry for the formula, I'm going to just have two terms in my training objective. You have to give the answer correctly. This is the first part of my objective. The second part says you have to be consistent with these logical constraints. So for the people who have a background, when we want to train the models with this kind of objective, usually, or this is what called loss function. This loss function needs to be differentiable because this is how the deep models work. They take the derivations and back propagate the errors. But now if I'm integrating the logical rules in my objective and try to avoid violation from the logical rules, the logic is usually not differentiable. That's why we try to make it a kind of soft logic translation or surrogate that we can make our objective differentiable. When we did that, so basically this also has kind of different techniques. We can go from logic to min-max, or we can go to some product. We have different ways of translating from hard like logic to the soft version of it that is differentiable. When we did that, then we can simply use this objective for tuning the model. And this is whatever language model that you're having. We have basically tried to augment this with this data and then further tune it. So with this, actually, I'm just going to share some of the results that we had. Some interesting results I'm going to show here. This is actually, you see that there are a lot of numbers, but I'm going to explain briefly. You see this K 1 to 10. This means actually the number of hops of reasoning. For example, if I want to answer a specific question, A is above B, sometimes I need to connect A to C, C to D, D to E, and then infer what is the relationship between A and something. So if the depth of reasoning is larger, this is actually counts the number of steps of reasoning that you need, or number of connections that you need to make to answer the question. And you see if the depth is larger, then the model's performance drops. And then this is also like a couple of years ago that we did this experiment. You see that GPT-3 actually was really having a hard time to answer these questions. And then we try to tune with our techniques that we call Q chain. And with this technique, we realize that with deeper kind of levels of reasoning, we can actually do much better compared to GPT-3. We had some other observations with the realistic domain. This table is more on the realistic human data. And we saw that with the human data, we actually had little bit of improvement with this multi-hop reasoning tuning. So, and the reason is that with the human data, usually humans don't use these complex explanations. You have maximum 1 or 2 hops of reasoning. We don't do these nesting explanations naturally. That's why actually the model didn't show that much of improvement here. And we realized with the human data, we need more common sense information. And we saw that the actual GPT large models, GPT 3.5, GPT 4, they actually acquire a lot of common sense knowledge through like training data. And that's why with the human realistic data, they were doing better. Just to summarize the results that we had at the time, we saw that guiding the model training with spatial logic helps complex and nested reasoning, and we can do even better than very large models. However, if we have like kind of the setups that models need common sense and they are more realistic, the GPT family were doing better in common sense, where they were failing in multi-hop. Something that I didn't discuss is that sometimes in the neurosymbolic approach, like when you want to include the rules of reasoning explicitly in the model, sometimes you can actually map all your contexts and everything to a formal logical representation and use external logical solvers, mathematical solvers to solve the problem. And with this case, with the synthetic data, this is easier to map, so we could get a higher result. But again, with the realistic data, mapping the natural language to these formal representations that can be passed to these logical solvers was harder. So this is basically the gist of the results that we had. But then, apart from this multi-hop complex reasoning, there are multiple challenges, other different kind of challenges that the language models have for spatial reasoning in real world. And the next thing was going back to this frame of reference issue that we were trying to test and see, okay, we saw that the models actually have a problem for understanding the frame of reference and putting actually like the right to generating the right spatial relations. So here, when we say a woman with an apple in her left hand standing to the right of the car, usually we mean actually the car has right and left, because a car has back, front, and intrinsic right and left. And we want the woman to be on the right of the car, not the right of the image, right? So here you see that the model was actually failing to generate this. But then what do you think if we add basically the information about the perspective? Can the model follow this? If I say the woman to the right of the car, from the car perspective, what happens? So with this test, actually, I'm not sure what you guess, but here, if you see the same image, the model realizes, okay, there is some focus on the car. So it seems that in this image on the left, a larger proportion of the image is dedicated to the car, but the relationships is still the same. Errors are happening here. So this is actually the motivation for our next kind of work, that can we help or can we evaluate the models for this frame of reference understanding? And then can we help them to do better in this? So let me again do the definitions of what I mean by frame of reference more accurately. Assume that we have this sentence, a dog is in front of the car. So this sentence can be interpreted in different ways depending on the frame of reference. For example, the car, as I mentioned, has intrinsic front and back. So in this image, you see that the dog is in front of the car from the car perspective. So this is called external intrinsic, and the dog is outside the car. Here you see that we can say also the dog is in front of the car, but this is from the camera perspective. So actually you see this is the back of the car, but from the camera perspective, the dog is in front of the car. So this is basically relative to the camera, and this is still external. We can also have this, the dog is in front of the car in this image, but you see this actually, the dog is in the back from the camera perspective, but from the car perspective, the dog is in front, and actually the dog is inside the car. So basically we have a lot of ambiguity of the frame of reference, just if we just go with this one sentence. And this ambiguity depends on the properties of the object. So let me explain what I mean by the properties. Let's say if we have a case like car has a kind of intrinsic direction. It also has affordance to contain objects. So that's why we have more ambiguity in different cases. But we invented this naming. We can have a box case. The box is symmetric, so there is no intrinsic direction for the box, but it can afford to be container. So that's why, again, the inside outside might be ambiguous. So we have these four cases: co-case, box case, car case, and pen case, depending on the affordance and intrinsic direction, and we create this. Now we try to answer these questions, like how large language models handle this frame of reference problem. When there is ambiguity, how the language models actually interpret it, what is the bias that they are taking, and then can we improve them for dealing with this notion of frame of reference? So here is the way that we try to evaluate. We try to create some synthetic data with a very simple setting. So we have the object that we are trying to explain the location. We call it locatum. And we have another object that we try to use as reference object to explain the location of the locatum. Like look at the cat and dog. And we can say the cat, the locatum, is to the right of the dog, which is the relatum. Now we can generate different types of objects and different types of relationships based on the four cases that I explained in the previous slide. Now we have the ambiguous cases and clear cases. The clear cases include the cases that we actually explain the perspective in the text. We say a cat is to the right of the dog from the dog perspective. Just no room for ambiguity. We just explain the perspective. And then we create different kind of tasks. One task is image generation. If I'm giving you this text, can you visualize it? And we use gaming environment to actually put these images, synthesize them, and then we can actually create this data set that includes both text and the corresponding image. We can also generate question answering data set. We can create explanations like a cat is to the right of a dog from the dog perspective and so on. Now we can ask where is the cat from the dog position, or where is the cat with respect to the dog from camera perspective. So we can actually switch the perspective in the question. Then this data set can help us to evaluate, can the model actually switch and shift the frame of reference focus. So some of the results that I want to share with you here is there are a lot of numbers. Sorry about that. I'm just going to highlight some of them. So we see that we have multiple models, and here is actually the test is done on the ambiguous cases. For the ambiguous cases, multiple answers are possible. So that's why the accuracy is not important actually that much. We just want to say when the model takes a specific answer, from which perspective that answer is correct. Relative is the camera perspective, and intrinsic is the real object intrinsic perspective. And for example, look at QN2, 72 billion. You see that the model is taking large proportion of the times, the model is correct when taking relative perspective. So it means these models actually are doing much better with the camera perspective. And then we also observe that the models actually are correct when the actual relation is just simply mentioned in the text. Like if I explain the cat is to the right of the dog, whatever question that I ask, the model just picks the right and answers with the term right. So it does just the keyword extraction, and it's correct from that perspective. If we do chain of thought, when you ask the model to think and do reasoning and then respond to me, it seems the behavior a little bit changes. So the number 3 is actually chain of thought that you see before chain of thought, the model just does more relative perspective. With chain of thought, the model still try to think a bit. It is not always necessarily better responses, but the model actually doesn't do direct extraction, which is a good sign. The model adds these things to do a little bit better. One very interesting result was that also that we see that, for example, models like Llama that is purely trained with text has no preference. Like it's kind of 50-50, changing between relative and intrinsic. And we see that this is the reason is that the vision models train mostly with captioning data that is 2D, and the explanations are generated usually from camera perspective. Like the very first image that I showed you in the beginning of my talk, the bicycle to the right of the Asian woman, actually, if you sit on the if you put yourself in the position of the woman, the bicycle is on their left, but from the camera perspective, the bicycle was on the right. So that is why even the captioning is based on 2D. And that's why, from the camera perspective, that's why the model that are trained on the vision have a more bias towards this camera perspective, which can be actually problematic if we are going to deal with real world situations and embodied or situated spatial understanding. So this was interesting. We also tried to see how we can actually help the model to do better image generation by looking at the perspective. Here, again, we try to actually explain to the model the types of the frame of references, the type of spatial relationships. This relationship is about distances. This is about directions. This is about topology. So we try to give the model better abstractions in the context, and then try to generate the layout of the image before generating the image. If the model is able to generate the layout correctly, then we have diffusion models. Some of the diffusion models are called layout diffusion models. And if I give the layout in addition to my textual explanation, then I will get more correct images. So, and our kind of frame of reference notion and explaining this in the context actually help the model to do better diffusion based on the layout. So we also further kind of continue this direction. Maybe we can actually do some image editing and edit the images that are originally generated by the diffusion models, and then try to edit them to respect the frame of reference. This framework is also something based on the previous work, established based on the previous work. And in the previous work, this image editing framework is actually working like that. You first ask the model, given the explanation, generate the first image for me. So a chicken is on the left of the chair from the chair view. You generate this, but then you try to analyze this image to see if it is correct or not. So you try to use we try to use the large language models to get the layout from the text only. So we get, like, for example, there is a chicken, the bounding box of the chicken has its coordinates, and the chicken is facing right, and so on. So we get this from the text. We also analyze the first generated image and try to do object detection, depth detection, orientation detection, and get another layout from the visual processing. Now we want to compare the visual processing, like representation, like the layout representation, compared to the textual inferred layout representation, and then get the difference between these images, generate a program that says you have to delete the chicken, you have to move chicken one to the right, and then we can do edit of the latent space of the diffusion model and regenerate image with our edits. So what we add on top of the previous work is that the previous work didn't look at the frame of reference and the depth information and orientation information. So we try to actually try to respect to the frame of reference that is mentioned in the text, and try to generate corrections that actually look at this frame of reference kind of interpretation, and then try to modify the latent space to respect this frame of reference information in their edits. So this is actually, we get a lot of positive results here compared to the existing models. Is called stable diffusion or Flux or GPT-4o. Our model is called For Sale, and this image editing framework can be repeated multiple times. You can generate the image one round and second round, and we do 3 rounds here. And every round we can see a little bit of improvement in the generated image here compared to the state of the art. So now with these two, I explained like multi-hop reasoning, frame of reference, but now I'm going to talk about more the issue of generalization, compositional generalization. Sometimes we have this basic concept, but then when we put them together, the models have hard time to generalize. Let me explain what I mean by generalization a bit more. So you have seen this setting already in my talk. We have this visual question answering again. You have the image and the question like how many blue squares are to the left of a large red sphere. Assume that the model actually understand this is a sphere or understand these things are red or understand what is blue. But when we put them together, blue square to the left of the large red sphere, and we want to count, this is actually composition of the many basic concepts like object, attribute, spatial relations, and counting. We actually see that the models, even if they know the basic concepts, they have a problem for compositional generalization. They cannot understand the complex compositions. We have also another example case here. When you say point to the blue square, that is in the same column as the yellow square. So you have an analogy and you want to find a column that has specific properties. This problem becomes compositional and the models actually have a hard time to solve this problem. Some interesting observations are that, for example, when you see you train the model with objects that are in this corner, and you have blue objects in this corner, but you don't have them in the training time, the model actually fails. Even it knows the blue color. When the blue color in this place is not observed during the training, the models actually have a hard time to recognize it during the test time. So this is really unexpected. So these basic skills and not generalizing to a little bit of composition of the cases is really some problem that people try to create tests for it and try to improve it. So the key issue of generalization is that I want to be able to solve the problems or configurations that I didn't see in my training time. I want to be able to solve them at the test time or deployment time. So one framework that we actually follow to this problem is based on previous work that is a paper called What's Left in Josh Tannenbaum group. The framework is as follows. I'm briefly explaining this framework and I explain you how we extend on top of this. So basically you have this now with large language models, we have the luxury that we can actually go from the natural language expressions and do some kind of semantic or formal representation. For example, if I can have this sentence point to the blue square, I can map it to a logical program that says x is blue x and square x. I want the x's that x is blue and x is square. So I'm going to get this program that actually says I need to compose blue and square properties and these two properties to get the one that I want. And then we have this visual side of the model that has a perception module. Let's say the visual processing gives me 10 or 20 bounding boxes. And now I want to actually check those bounding boxes individually. Say, for example, bounding box 1, is this blue or not? Bounding box 2, if this is blue or not. And then I'm going to check also square, if this bounding box is square or not, and so on. So this is kind of logical predicates here. And I can say this logical predicate actually can be a neural model simply that gives me a probability of this bounding box being blue or not blue. So basically I can get a probability distribution for each of these predicates and I can have like models trained to tell me these probabilities. And now I can actually handle these probabilities and uncertainties, compose them, and them together explicitly with different logical, or here we do soft logical operations to be able to find the box that has the highest probability of being blue and square at the same time. So in this case, we don't want the model to learn the composition. We do the composition explicitly. As far as the model does the perception level or the atomic concept level recognition, then we can do the composition in the program and then the compositional generalization solved in a symbolic way. So basically, that is the gist of it, the key message. Like we learn the concepts, we deal with the uncertainty or extract the uncertainty at the perception level, and we do the compositional reasoning in the program, probabilistic program, explicitly. So this is a framework that we build on top of it. There are some issues with this framework. For example, this is a very bad bottleneck here. If I want to have a model for every single predicate, like blue has a separate model that I'm going to train to learn blue. I have a sphere that has a separate model, and these models are tuned and trained with data to be able to recognize this kind of concept. However, when we come to the natural language processing, we have a lot of words and synonyms that can mean the same. When we use this formal representation, the connection between those words is lost. So basically, blue and light blue and dark blue, maybe they are very similar. But when I'm going to generate logical predicates, my logic doesn't know that blue and dark blue are similar. However, if you're going to the neural space and embedding a space, the distributed or vector representation of the similar words are actually similar. Then if I learn blue, then maybe I can recognize light blue as well because their representation is similar. So going with this idea, instead of training a model for each predicate, logical predicate, we actually combine the embedding or distributed representation of the predicates with the representation of the visual bounding boxes. We combine them and pass them to this multimodal model that actually gives me this probability distribution of blue bounding box. And if I do light blue bounding box, then again, I can just do the same thing. And even if I haven't observed the light blue, maybe the model still says, okay, this is perhaps something close. So this gives us a lot of flexibility, and we can get a lot of improvement in this data set. These data sets are invented for testing this compositional generalization. That's why you say this is a Kelver data set, and CoGen is the compositional generalization test split. And this split is the compositional generalization test. You see that it is much lower than just normal testing. The normal testing with this data set is simple because the models can just remember everything. But if we do the novel compositions, first of all, the accuracy is much lower, and we also can improve with our framework, which is called NESI-COCO in this case. With this dataset, we have even more challenging compositional generalization test, and we get 5% improvement here. With the variety of language, we can actually replace the term cube with box, sphere with the ball. So we can just generate more synonyms in our test set. And then we see that actually the previous models have really hard time when we have variety of language and replacing the words with their synonyms, while NESI-COCO actually is very robust or doing reasonable accuracy still with the variety of language. So one recent work that we are trying to go even step further for this neurosymbolic and explicit composition is that let us actually not be limited to this probabilistic program and this kind of syntax that the models, the large language models, are less familiar with it. We realize that for the complex questions, sometimes actually going to this formal representation is hard for the models. But if this formal representation is just Python code, then the models are trained a lot with Python. So maybe mapping to Python code is better than mapping to these probabilistic programs and this kind of more domain-specific representations. So that's why in this our new work, we actually tried to change several things in this framework. One is that I'm using the large language models to generate Python code. And then I'm going to actually have this, another thing is that we have these all large models like 20 billion, 75 billion, 8 billion models. Why not just use those and then use them as building block and try to compose their atomic skills in the program. So that was the two main ideas that we followed here. And we saw that actually now, if I'm going to explain this program a bit, you ask the language model, is the object in the rand bounding box a sphere? You get a probability, and this probability is going to a Python variable. And then I'm asking, is the object is a small? And I get the probabilities, oh, it goes to Python variable again. And then we have our soft logical operations, like I want the sphere X and the small x. So I want to the composition of the two. And then we get the small sphere probability for every bounding box. And we can have the luxury of for loops, if structure. So we have the capacity of Python, full capacity of Python to do more complex programs here for more complex queries. And then we see actually now, we call this neuropythonic. Basically, our symbolic representation is more Pythonic. And we see actually a lot of very surprising improvement in some domains that the models might not have seen in their training data. One of these domains is referring expression, or ref GTA. The problem is, like you say, a man with red shorts and red and beige striped shirt, and the model needs to draw a bounding box around the man in this picture. So this happens to be, actually, we see that many models fail to actually solve this problem. Like we have InterVL 8 billion does only doing 6% accuracy, and 1 billion does 2% accuracy. But with our model, we call it Neptune, we can actually get to basically 69% accuracy with 8 billion. And if we fine tune the 1 billion, we can get accuracy similar to 8 billion. So with the smaller models and this Pythonic composition, we can actually beat or compete with the larger models. So this was really an interesting result. So this was about compositional generalization, but just to point to another direction or relevant direction that we do for spatial understanding. I see that there is no time to go to the detail of this, but in my group, we also try to use the same ideas of skill-based training for vision and language navigation. So I'm just explaining this problem briefly. So you have an agent receives natural language instructions and then tries to follow like visual environment by going to the, for example, take a right out to the kitchen, and the agent needs to select the view that is related to the instruction and go forward. And again, the agent takes the trajectory until it gets to the target, that is basically dining room table in this instruction. So we have been working a lot to solve this problem from different perspectives and different solutions. And one thing that we're trying to push is that, okay, maybe again, we have to train the model to do the basic skills. Like the model needs to understand the directions, understand the vertical movement, like go upstairs, understand the landmarks. If I say table, that it should recognize that I need to recognize the table. So we try to actually tune the model for different skills and then try to compose the skills for following complex natural language instructions. So I don't go to the details of this, but also we have a paper under review recently for this, and we get some interesting results. We do also in situated environments, like with 3D representations, and we try to actually also make the model to understand like different perspectives, different objects, low-level properties. Again, this is a benchmark data set that we published just this year. And I'm going to close my presentation with 2 minutes briefly describing this idea of neurosymbolic framework. So I didn't mention the term neurosymbolic, but just to give you an idea, when I explained the integration of the rules of spatial reasoning, like left A, B, this is actually symbolic knowledge that we try to integrate in our modeling. When we map to probabilistic program, we do explicit probabilistic reasoning. We use the neural model to get to the program. This is what I call neurosymbolic. However, these models, if you want to actually integrate this logical reasoning with the neural models, we don't have a lot of libraries and frameworks that help us to do this programming. Despite, actually, when we do deep modeling or interfacing with large language models, there are a lot of tools and APIs that we're going to use, but the symbolic techniques, we don't have a lot of this. That is one bottleneck that makes the community less going to use these neurosymbolic hybrid approaches. And that is why one of my actually ambitions has been like, can I build a really generic framework and neurosymbolic framework that people can write their own logical knowledge and then connect to separate rules and combine with neural modeling easily. So that is a framework that we have developed, and it's called Dominoes. This is for designing complex models, combining the ideas of thinking fast, thinking slow, that you do actually neural computations perceived as kind of fast computations, and search-based or logical-based solutions as kind of slow solutions. We want to combine these two paradigms in our modeling design. So I'm going to just skip the explanation. I can share the slides for people who are interested to learn about this framework, the type of algorithms that we have underlying this framework, the way that you write the program in this framework in designing a graph and then writing your logic, like I want this concept to be disjoint and so on. We have also a demo that you can take a look at this. So to conclude my talk, I explained the spatial reasoning from the perspective of multi-hop or complex nested reasoning, from the perspective of looking at different frames of references. And I looked at the more general compositional generalization with symbolic reasoning, and pointed briefly to the skill-based navigation problem and the general framework of neurosymbolic, with the hope that we can develop this framework for democratizing more hybrid approaches for solving AI problems. These are the type of researches that I'm doing in my lab in general. I point to some of this research in my group, but feel free to look at our research extended. We also have a book on spatial language understanding published last November. And with that, I'm going to thank my students who helped doing all this research and my sponsors here. I'm open to the questions. Thank you very much for listening.
That is a fantastic talk, Parisa. That's so awesome. With consideration of time, I'm going to get to the question and answer right away. So, Parisa, you also have access to the question, but for the sake of our audience, for those who are listening, the first question is from, I assume, Arshad. His question is this instruction tuning format to integrate these rules, are they context for the prompt before the instruction pair?
I assume this is in the context of my spatial reasoning rules, and those are not, in this case, those are not in the context. They are actually a separate set of rules that we're having for generating a source of supervision. So in the context, I have basically the explanation of the scene, I have the question, and the model is actually learned, hopefully, to get the abstraction that has this more patterns of logical reasoning during the training. So this is the hope that we are trying to follow in that specific work. So the rules are not in the context in that case.
Wonderful. And so the next question I have is, do you think expanding the richness of multimodal representations will help to overcome frame of reference limitations in visual LLMs? Or is there a risk that added complexity could further destabilize the model's spatial grounding?
Very great question. So actually, I think we have this concept. I mean, if we want these models to operate in the real world, we have to make them trained or learn to deal with this frame of reference. So we cannot get rid of this concept if we want these models to have the situated understanding. That is one thing. But then, of course, whenever we are going to have more complex or rich concepts for the models, then, of course, if we don't have enough data, the models become a bit kind of at risk of being less stable and being like kind of again, we need to, if we want to follow the paradigm of, okay, give them more and more data, then of course we have to have enough data with the situated environment and realistic environments to help them to understand this frame of reference. That is why actually I'm going to conclude again now, that is why I'm encouraging doing neurosymbolic, because we can actually teach the models with less data to focus on the concept learning, maybe in the simplistic setting, but then in the complex setting, you need the composition then you can do symbolically compose this concept together and have a more trustworthy way of solving the problem, if that makes sense. That is my idea. So that's why I mean, at some point you have less data, exploit the symbolic reasoning more. If your data is enough to really deal with the problem, you need less symbolic modeling, and this is always a transition kind of paradigm.
Thank you. And so we have a couple of more questions. You know, many of our audience work in the medical domain, and we have a question for you that we're very interested in the approach you presented for compositional generalization. Do you think that's something that has potentials to be addressed in the medical domain as well?
Certainly, absolutely. Actually, the spatial information, specifically, I had a colleague working on this spatial in medical domain with medical images like X-rays or like kind of different kind of medical images, and trying to really analyze the image and understand the spatial relationship between different kind of patterns in the images and try to interpret that. So I think we always have this compositional generalization as well there. If I'm going to limit it to the instrument that I'm using for taking the images, medical images, right? And if my model just works with this specific lab type of images, that will be problematic. Whatever model that I'm training here doesn't work for other type of images or doesn't work tomorrow. I have to again generate more and more data with every instrument, or new cases that maybe we didn't have a lot of them before, then we cannot really do a good diagnosis in those cases. So that's why I think compositional generalization is really important to make an abstraction that helps doctors with their like domain knowledge to really get a diagnosis. We need to have those kind of general abstractions that denoise and really look at the actual essence of the information in the images for better compositional generalization.
Wonderful. So I'm going to have one last question. It's from Stephen Sway. So in the multi-agent systems that you have presented at the end of your lecture today, how exactly was each agent prioritized when performing a particular task?
So I assume this is referring to my navigation stuff, if I'm correct, because in the other cases we had only one backbone. But in the cases that we tuned the backbone, we actually exploited the large language models themselves to recognize. We try to actually, the model are good to do natural language processing, reordering the instruction and say, okay, now you need to go to the table. And then actually we prompt the model, okay, going to the table means you need to recognize a landmark. And the model actually, the language model itself can help me to do routing. We didn't tune the router in this case, but potentially this can be also tuned. But in this case, with the spatial navigation stuff, the routing was effective to delegate the task to the right expert. So in these agentic systems, I think we can exploit these language models themselves. And I think now it really gives us a more capacity to do this kind of routing, task delegation, or even symbolic representations with the language models themselves for these hybrid approaches.
So I have one last question from our audience. He or she says, this year we have the language diffusion model that's been presented. Have you considered about using the diffusion model to do the reasoning task? Because diffusion has bidirectional unmask instead of next token prediction that has auto regressive models. What are your thoughts and how to capture the global features better?
Exactly. I think this is really a great question, and this is actually a research direction that I am exactly following with two of my students working on this. We actually, I am very also excited about the capability of the fusion models to get the look at the global information, not doing just autoregressively next token prediction. And I think they have two capacities. One is like looking at this information at the same time. And the second is like, okay, the noising can actually be used for giving me a more clear line of reasoning, and even doing like symbolic chain of reasoning. That is some ideas that I am. It has a level of ideas and some initial experiments, but that is actually something that I'm very excited about. Thanks for the question.
Yeah.
Okay, and with that, I'm going to hand it back to Jack for closing. Thanks again.
Thank you, Pepe.
Thank you
And
so
thank
much.
you, Dr. Kordjamshidi. That was an amazing presentation. I think some of the answers to these fantastic questions really underscore the importance of cross-disciplinary collaboration between, AI during development so that with clinicians and, domain-specific medical practitioners so that we get all that nuance, so we get all this compositional generalization, hashed out. Well, thank you very much.
Thank you so much for having me again. It was really a great pleasure.
Thank you all for attending, sticking around.
Thank you. Bye bye.